So here we get, for an x belongs to u, modulus of g of tx minus gk of tx less than epsilon naught. Now we are going to come to the conclusion point. We have to prove that for every g belongs to b, there exists gk belongs to be such that norm of t cross g minus t cross gk less than epsilon. So epsilon naught. So for any g belongs to, we are considering norm of t cross g minus t cross gk. Then by the definition of norm of an operator, we get this is equal to supremum norm x equal to modulus of t cross g minus t cross gk of x, and this is equal to supremum norm x equal to modulus of t cross g of x minus t cross gk of x. Then definition of t cross g of x equal to g of tx. So we can say that this is equal to supremum norm x equal to modulus of g of tx. T cross g of x is equal to g of tx minus t cross gk of x equal to gk of tx, and this is less than epsilon naught from this representation. Modulus of g of tx minus g of tx, gk of tx less than epsilon naught already we have proved, and from this supremum is also less than epsilon naught. So here we get supremum norm x equal to this less than epsilon naught. That is, we get modulus of t for every g belongs to b, there exists t cross belongs to gk belongs to b such that norm of t cross g minus t cross gk less than epsilon naught, and this says that set t cross g1, t cross g2, etc. t cross gm is an epsilon naught net for t cross b. Implies t cross b is totally bounded because epsilon naught is an arbitrary positive real number, and here we get a finite epsilon naught for t cross b, and hence t cross b is totally bounded, and hence total boundedness implies relatively compactness. That implies t cross of b is relatively compact because x dash is complete. Okay, and this says that t cross is compact. Then next we are going to see theorem 8.31 in section 8.3. Eigenvalues. The set of eigenvalues of a compact linear operator t from x to x on a normed space x is countable, perhaps finite or even empty, and the only possible point of accumulation is lambda equal to 0. That is, we have to prove that the eigenvalues of a compact linear operator t from x to x on a normed space x is countable. Sometimes it may be finite also, even empty, and the possible point of accumulation lambda equal to 0 only. That is, we are going to show. So we are going to prove that eigenvalues, set of eigenvalues is countable. For this, we know that eigenvalues of a linear operator is set for lambda belongs to sigma p of t. That is, the elements of point spectrum are known as eigenvalues. Or also we know that lambda is an eigenvalue of t, means there exists x not equal to 0 such that tx equal to lambda x. Okay. So we are going to prove that for every real number k greater than 0, lambda, set of all lambda belongs to sigma p of t such that modulus of lambda greater than or equal to k is finite. So we have to prove that sigma p of t is countable, or set of all lambda belongs to sigma p of t is countable. For this, we are going to show that for every real number k greater than 0, set of all lambda belongs to sigma p of t such that modulus of lambda greater than or equal to k is finite. And for each real number k, we can consider the next natural number, and we can write this sigma p of t as the union of set of all lambda belongs to sigma p of t such that modulus of lambda greater than or equal to k, and finite countable union of finite set finite be obtained. Okay, so it is enough to prove that for every real number k greater than or equal to 0, set of all lambda belongs to sigma p of t such that modulus of lambda greater than or equal to k is finite. Suppose this is not true, we are assuming that this is not true. That means there exists a k naught greater than 0 such that this result is not true for that k naught. That means there exists a k naught greater than 0 such that set of all lambda belongs to sigma p of t such that modulus of lambda greater than or equal to k naught is infinite. Finitely, not finite. That means infinite. That is, there is infinitely many lambda in sigma p of t. That means there is a sequence, infinite sequence lambda n of distinct eigenvalues of t such that modulus of lambda n greater than or equal to k naught. That is, modulus of lambda greater than to k such a lambda is set of lambda is infinite. So we can find a infinite sequence of lambdas in sigma p of t, say sequence lambda n, which are distinct eigenvalues of t and satisfying modulus of lambda n greater than or equal to k naught, because lambda is replaced by sequence lambda n and k is replaced by this particular k naught. So we can say that there is a sequence lambda n of distinct eigenvalues such that modulus of lambda n greater than or equal to k naught. Last we are going to get a contradiction because our assumption is there is no, this result is not true. So we are going to get a contradiction again. Okay. So we know that lambda is an eigenvalue of t if tx equal to lambda x for some x not equal to 0. And here lambda is an distinct eigenvalues of t implies there exists lambda xn such that lambda in txn is equal to lambda in xn for some xn not equal to 0. So this implies txn equal to lambda in xn for some xn not equal to 0 for every n. Then, and also we know that eigenvalues of a linear operator is linearly independent. Eigenvalues are linearly independent. So we can say that these set xn's are linearly independent. Set of all xn's are linearly independent. Then we are considering span of first n vectors of these eigenvectors. That is mn is equal to, and denoted by mn, that is mn is equal to span of x1, x2, etc. xn. The span of the set of first n vectors in this eigenvectors. And we know that span of a set is a subspace. So Mn is a subspace of capital X. And for each x belongs to Mn, we can say that X is optimum. We know that span of a set is the set of a linear combination of the vectors in that set. So span of x1, x2, etc. xn is every element of this span of x1, x2, etc. xn, that is every element of Mn is like this, is a linear combination of this x1, x2, etc. xn. So we can say that for every x belongs to Mn, x can be written as some alpha 1 x1 plus alpha 2 x2 plus etc. alpha in xn, where alpha 1, alpha 2, etc. alpha n are scalars. Then we are considering that this representative is denoted by equation 1, that is of later use. X equal to alpha 1 x1 plus etc. alpha in xn, that is denoted by 1, that is for every x belongs to Mn also. Then we are considering t minus lambda n I of x. We know that tx equal to lambda x and txn is equal to lambda n xn. So txn minus lambda n xn equal to 0 also. So we are applying here t minus lambda n I of x, or apply t minus lambda n I on both sides of equation, that is actually going to see. So we are applying t minus the operator t minus lambda n I on both sides of equation 1. Then we get in the left hand side t minus lambda n I of x equal to the right hand side t minus lambda n I of alpha on x1 plus etc. alpha in xn. Then expanding on the right hand side we get this is equal to t of alpha on x1 t minus lambda n I of alpha on x1, and we know that t and identity operator I are linear. So we can say that t minus lambda n I is also linear. So we can say that t minus lambda n I of alpha on xn is nothing but alpha 1 into t minus lambda n I of x1, and this is equal to t x1 minus lambda n x1. So alpha 1 into t x1 minus lambda n x1. Again second time alpha 2 into t x2 minus lambda n x1 etc. plus last term alpha n into t xn minus lambda n xn. Then just a substitution for t xn is equal to lambda n xn. So we can say that this t xn x1 can be written as lambda 1 x1 etc. t xn can be written as lambda n xn. So this is equal to alpha 1 into lambda 1 x1 minus lambda n xn, that is lambda 1 minus lambda n into x1 plus alpha 2 into lambda 2 x2 minus lambda n x2, that is equal to lambda 2 minus lambda n into x2 plus etc. last term alpha n, the term next previous to last term is alpha n minus 1 into lambda n minus 1 minus lambda n into xn minus 1, and the last term is alpha n into lambda n xn minus lambda n xn, that is equal to 0. So the last term becomes 0. So we get alpha 1 into lambda 1 minus lambda n into x1 plus etc. alpha n minus 1 into lambda n minus 1 minus lambda n into xn minus 1. And here alpha 1, lambda 2, etc. lambda n are scalars. So we get alpha 1 into lambda 1 minus lambda n is a scalar. Alpha 2 into lambda 2 minus lambda n is also a scalar, etc. Alpha n minus 1 into lambda n minus 1 minus lambda n is also a scalar. So we can say that this right hand side is a scalar linear combination of x1, x2, etc. xn minus 1. That means for any x belongs to Mn, we get t minus lambda n I of x is an element of is a linear combination of x1, x2, etc. xn minus 1. And also we know that linear combination of x1, x2, etc. xn minus 1 is in the set span of x1, x2, etc. xn minus 1. And from this representation, we can say that span of x1, x2, etc. xn minus 1 is nothing but mn minus 1. So we can say that this belongs to xm minus 1, the right hand side. And thus that says that for each x belongs to Mn, t minus lambda n I of x equal to this, and this belongs to Mn minus 1. So for every x belongs to Mn, t minus lambda n I of x belongs to Mn minus 1. And this together denoted by equation 2. For every x belongs to Mn, t minus lambda n I of x belongs to Mn minus 1 is denoted by equation 2. Then we are going to, we get Mn. Mn is span of x1, x2, etc. xn. For each natural number n, we get Mn. So we get a sequence of subsets Mn like this. And we know that this is a finite dimensional subspace of x because span of x1, x2, etc. xn has dimension less than or equal to n. So definitely this is a finite dimensional subspace of x. And we know that every finite dimensional subspace of x is closed. So we can say that each Mn is closed. And we are writing like this because we are going to apply Rees lemma. And Rees lemma says that if y and z are subspace of a normed space x and y is a proper and closed subset of z, then for every theta in this interval open interval 0, 1, there x, and for any theta in open interval 0, 1, there x and z belongs to z such that for every norm z is equal to 1 and for every y belongs to norm of z minus y, norm of z minus y greater than or equal to theta. That is the statement of Rees lemma. So we are going to apply Rees lemma. So we have to get a subset and a superset. And subset is a proper subset also. So here Mn and Mn minus 1 are considered. And we know that Mn is span of x1, x2, etc. xn. So definitely Mn minus 1 is span of x1, x2, etc. xn minus 1. And xn is not an element of Mn minus 1. So definitely Mn minus 1 is a proper subset of Mn. Moreover, span of a set is a subspace. So Mn minus 1 is a proper subspace of Mn for every n. And we are applying Rees lemma for Mn and Mn minus 1. Then by Rees lemma, we know that Mn minus 1 is a Rees lemma says this: y and z subspace of x and y is a closed and proper subset of z. Then for every theta in this interval, there exists z belongs to z such that norm z is equal to 1 and norm of z minus y greater than or equal to theta for all y belongs to. Here y is replaced by Mn minus 1 and z is replaced by Mn. So there x and z belongs to an element of Mn also. So we get by Rees lemma there x and yn belongs to Mn. Mn element of Mn is denoted by yn. There exists z is replaced by yn. So there exists sequence yn because Mn minus 1 is closed and proper subset of Mn for every n. For each natural number n. So we get for each natural number n we get an element z. So name it as yn. So for every n we get a element yn in Mn. So we get a sequence yn. So by Rees lemma, there exists sequence yn, that is repeated application of Rees lemma. There is a sequence yn such that yn belongs to Mn and norm of yn equal to 1. Here yn is instead of z. And norm of yn minus x greater than or equal to 1 by 2 for all x belongs to Mn minus 1 because theta is taken as 1 by 2. So we get this together we denote it as equation 3. There is a that is norm of yn minus x greater than or equal to 1 by 2 for all x belongs to Mn minus 1 is denoted by 3. Okay, here we get a sequence yn such that norm yn is equal to 1. And we are going to we have to get a contradiction actually. So we are going to get a contradiction to the statement, the condition given in the statement that T is a compact linear operator. So we know that T is a compact linear operator means this theorem says T is a compact linear operator if and only for every bounded sequence xn in X, Txn has a convergent subsequence. This is a characterization of compactness theorem 8.13, and this says that T is compact if and only if every bounded sequence xn, Txn has a convergent subsequence. And here T is a compact linear operator, so for every bounded sequence xn, Txn has a convergent subsequence. And here the sequence yn is a bounded sequence because norm of yn is equal to 1. So we are going to prove that, we have to get a contradiction. So we are going to prove that sequence Tyn has no convergent subsequence. For this we are going to prove that, claim that norm of Tyn minus Tym greater than or equal to 1 by 2 into k naught for n greater than m. So we are going to prove this because from this result we can say that sequence Tyn cannot have a converging subsequence because this is against the condition of Cauchy sequence. And know that every converging sequence is Cauchy. So this says that sequence Tyn is not Cauchy, and so also any subsequence of sequence Tyn is not a Cauchy sequence, because if it is a Cauchy sequence we have to say that norm of Tyn minus Tyn less than 1 by 2 into k naught. So this we are going to prove this is greater than or equal to 1 by 2 into k naught for any n greater than m. Then we get a contradiction. So we are going to prove this. Okay, so we are considering Tyn minus Tym and introducing lambda in yn. That is Tyn minus Tym is equal to Tyn minus lambda in yn plus lambda in yn minus Tym. Just introducing lambda in yn minus lambda in yn and plus lambda in yn. So Tyn minus lambda in yn plus lambda in yn minus last term Tym. Then we are going to use this equation 3 to get a contradiction. Okay. For this we are norm of Tyn minus Tym is like this. Then this can be written as lambda in yn minus x tilde, because in equation 3 we have norm of yn minus x greater than or equal to 1 by 2. We have to get norm of Tyn minus Tym greater than or equal to 1 by 2 into k naught. That is you have to get. Here we have norm of yn minus x greater than or equal to 1 by 2 for all x belongs to mn minus 1. Because of that reason we are writing this in terms of yn minus some vector x tilde. And here the term having yn is lambda in yn. Here lambda in is a scalar. So scalar multiple of yn is no problem. So we are considering lambda in y. This can be written as lambda in yn minus x tilde, because this particular term lambda in yn minus the remaining 3 terms is denoted by x tilde. So this is equal to lambda in yn minus x tilde, where x tilde is equal to lambda in yn minus 1 becomes Tym minus Tyn plus lambda in yn, or x tilde is equal to lambda in yn minus Tyn plus Ty. That is, we are writing this all other terms except lambda in yn having reverse opposite sign. That is, minus lambda in yn becomes lambda in yn, plus Tyn becomes minus Tyn, minus Tym becomes plus Ty. So x tilde is equal to lambda in yn minus Tyn plus Ty. Or simply substituting here lambda in yn minus x tilde, substituting for this x tilde we get this right hand side of this equation. So x tilde is like this. Then for applying this equation 3 we have to get norm of this greater than or equal to 1 by 2. So norm of this greater than 1 by 2 into k naught if, and we have from equation 3 norm of yn minus x greater than or equal to 1 by 2 if x belongs to mn minus 1. So here we have to get norm of lambda in yn minus x tilde greater than or equal to 1 by 2 into 1 by 2 if x tilde belongs to mn minus 1, comparing to equation 3. So we have to prove that x tilde belongs to mn minus 1 for m less than n. Let m less than n, we claim that x tilde belongs to mn minus 1. For this we consider first Tym, the term Tym alone. Then first we are going to show that Tym belongs to mn minus 1. Then we are going to show that the first and second terms together belongs to mn minus 1 by using equation 1. Okay, first we consider Tym. claim Tym belongs to Mn minus 1, and we know that Ym belongs to Ym belongs to mm, that we know from the construction of this sequence Yn such that Yn belongs to Mn. That means Ym belongs to mm. This is for every n. Okay. So Ym belongs to mm, we know that, and we have to prove that Tym belongs to Mn minus 1. So mm is contained in m. We take m less than n. So mm contained in Mn. That we know. Again, m less than n implies m less than or equal to n minus 1. Because we have to compare with the m and n minus 1. We have to prove that Tym belongs to Mn minus 1. So compare m and n minus 1. So m contained in Mn since m less than n. Also m less than n implies m less than or equal to n minus 1. So m contained in Mn minus 1. We have to get Mn minus 1. So m comparing to n minus 1. So we get m less than or equal to n minus 1 implies m contained in Mn minus 1. Again, Ym belongs to mm, that we know from this construction of the sequence. Ym belongs to mm implies Ym belongs to Mn minus 1 because m contained in Mn minus 1 implies Ym belongs to Mn minus 1, and we know that Mn minus 1 is equal to span of x1, x2, etc. xn minus 1. That means this Ym is a linear combination of x1, x2, etc. xn minus 1. And actually we have to get Tym belongs to Mn minus 1. Here we get Ym belongs to Mn minus 1. Then Tym belongs to Mn minus 1 because Txj is equal to lambda j xj. And we know that Ym is a linear combination of x1, x2, etc. xn minus 1. That means Ym is equal to some alpha on x1 plus x2 alpha n minus 1 xn minus 1. Then T of Ym becomes alpha into tx1 plus etc. alpha n minus 1 into txn minus 1 and txj lambda j xj. So we get alpha 1 into lambda on x1 plus etc. 4. So we get definitely Tym belongs to Mn minus 1 since txj is equal to lambda j xj. Thus we get the last term Tym belongs to Mn minus 1. Now we are going to show that the first and second terms together lambda n yn minus Tyn belongs to Mn minus 1. For this consider lambda n yn minus Tyn and using equation 2. Here we have equation 2 is this t minus lambda n I of x belongs to Mn minus 1 for all x belongs to Mn, and using this equation 2 we get the result. Okay, so we are considering lambda n yn minus Tyn, and this can be formulated in the form t minus lambda n I of some vector. So here we get this is equal to minus of t minus lambda n I of yn. Just expanding we get this minus, multiplying this minus and expanding we get t, this term becomes t lambda n yn minus Tyn because minus Tyn minus into minus plus lambda n yn. So nothing but lambda n yn minus Tyn. So this is can be written as minus of t minus lambda n I of yn because converting to the form like this equation 2. So this is, and this belongs to Mn minus 1 by equation 2 since yn belongs to Mn. From this construction yn belongs to Mn. So x belongs to Mn implies t minus lambda n I of x belongs to Mn minus 1 by equation 2. Here the vector is yn. So yn belongs to Mn, we know that, and so from comparing with the equation 2 we get t minus lambda n I of yn belongs to Mn minus 1, and definitely then minus of t minus lambda n I of yn also belongs to Mn minus 1 because Mn minus 1 is a subspace. So minus 1 scalar multiplication also an element of Mn minus 1. So the left hand side is also an element of Mn minus 1. That means lambda n yn minus Tyn belongs to Mn minus 1. Together we get x still belongs to Mn minus 1. So we are considering norm of Tyn minus Tym. From equation 4 we get norm of Tyn minus Tym is equal to norm of lambda n yn minus x tilde. And taking lambda n on outsides we get modulus of lambda n because a scalar in the outsides of norm becomes modulus. Modulus of lambda n into norm of yn minus, and in the second term x tilde there is no scalar lambda n. So we taking lambda n outside, we divide this term by lambda n or multiplying by lambda n inverse. So this is equal to modulus of lambda n into norm of yn minus lambda in inverse into x tilde. And from equation 3, that is this equation, we get norm of yn minus x greater than or equal to 1 by 2 for all x belongs to mn minus 1. Here x tilde belongs to mn minus 1. So lambda in inverse into x tilde also belongs to mn minus 1 because it's a scalar multiple. And mn minus 1 is a subspace. So we get norm of this greater than or equal to 1 by 2. Again, modulus of lambda n into norm of this greater than or equal to 1 by 2 into modulus of lambda n. Writing this modulus of lambda n in the position. Okay. Implies from the starting norm of Tyn minus Tym greater than or equal to 1 by 2 into k naught because modulus of lambda n greater than or equal to k naught we have taken. This modulus of lambda n greater than or equal to k naught. So we get norm of Tyn minus Tym greater than or equal to 1 by 2 into k naught where k naught greater than 0, positive real number. So this says that sequence Yn has no convergent subsequent because every convergent subsequent sequence is Cauchy, and since this cannot become a Cauchy sequence, and so this cannot have a subsequence which is Cauchy also. So this sequence Tyn has no convergent subsequence, and this is a contradiction to the high compactness of T because using theorem 8.13 and sequence Yn is bounded. Every bounded sequence Yn, Tyn has a converging subsequence by 8.13, but here we get Tyn has no convergent subsequence, but T is compact and Yn is bounded. So we get a contradiction. So our assumption, the set of eigenvalues there exists there is a k naught such that norm of norm of k greater than to lambda naught. Sorry, norm of lambda n greater than to k naught is infinite, or infinite is a wrong assumption. So the set of, that assumption is wrong. So we can say that the set of eigenvalues of T is countable. And from that we can say that also we can say that from the definition of accumulation points, the only accumulation point is 0 also. Then already we have seen in between a result ym belongs to mn minus 1, Tym belongs to mn minus 1. That because txj is equal to lambda j xj we have seen in midst of the proof, but here explain here is mn minus 1 span of x1 x2 xn minus 1. Ym belongs to mn minus 1 implies ym is equal to alpha on x1 etc alpha n minus 1 xn minus 1. Then Tym is equal to T of this. Then T is a linear operator, so this is equal to alpha 1 into Tx1 plus etc alpha n minus 1 into Txn minus 1. And Txj is equal to lambda j xj implies alpha 1 into lambda 1 x1 plus etc alpha n minus 1 into lambda n minus 1 into xn minus 1. And this is equal to alpha 1 into lambda 1 x1 plus etc. And alpha 1 into lambda 1 etc scalar. So we get a combination of x1, x2 etc xn minus 1 again. Linear combination of the vectors x1, x2 etc xn minus 1 that belongs to definitely mn minus 1. That is Tym belongs to mn minus 1. So this is used in the proof. Okay, thank you students. Sona. Net off agila.